All right, just a minute. So let us start with today's class. Let me share the. Is it visible to everyone?
Yes, sir.
Yes, sir.
So in the last class we have completed natural convection, and we are starting with boiling and condensation. So boiling and condensation is a very important topic, particularly in chemical and biochemical engineering, because if you look at most of the process applications, you will see there is a phase change of the fluid medium is going to take place. A typical example is if you try to heat some fluid, typically you use the steam to heat, usually condensed. Okay, because the whenever you are condensing the steam, the amount of heat transfer is much larger compared to if you are only looking at the sensible heat. Okay, so that is the reason why usually the saturated steam is used for heating purpose. Okay, all right. So as I said that many process application basically involve the change in the phase. And again, as I said that the rate of heat transfer in case of boiling and condensation is usually much higher, much faster than the rate of conduction and convection heat transfer. So whatever the rate of heat transfer you are going to see in conduction and convection, compared to that, if you see the rate of heat transfer in boiling and condensation is going to be much higher. The reason for that is usually if you look at conduction and convection, in the conduction and convection, the heat is transferred from the surface of the fluid to the bulk of the fluid, isn't it? So the resistance is very high, isn't it? Because you have to, the heat has to pass through the film as well as then it has to penetrate to the bulk. But in contrast to this, if you look at the heat transfer in boiling and condensation, in boiling and condensation, primarily the heat transfer takes place only in a narrow region very near to the surface, only in the narrow region, isn't it? Isn't it? So for instance, if you are boiling a water, let's say boiling a water, you can see that the whenever you are boiling the water, the heat transfer only takes place from the surface to the air, isn't it? Isn't it? Because rest of the places you will see the temperature is same, so that resistance is not offered there. All right. So again, even though the heat transfer is taking place in a narrow region, in case of the condensation and boil, still the convection is the major, convection plays a major role in the heat transfer. Okay, and typical examples of process application where condensation takes place, these are given here. So for instance, boiling can be used in power plants, reboilers, in distillation column, etc. Similarly, the condensation is there in the distillation column, condensation of steam for heat transfer in process plants, etc. Okay, so is it clear to everyone what we are trying to say? This is important in convection, conduction, and the heat transfer with phase change. The only point to note down is whenever there is a heat transfer with phase change, the rate of heat transfer is much higher. Reason for that is heat transfer takes place only in the narrow region near the surface whenever there is a phase change takes place, because the entire bulk remains at the same temperature. Remember, if water is boiling, the temperature of the water remains at Celsius, isn't it? It's not changing. So there is no temperature gradient present across the bulk of the liquid. Temperature gradient present only in the narrow region near the surface. Phase change is taking place. Can you see the point? Hello? Does it make sense what I'm trying to say? Okay. All right. Hello.
Sir,
Am I audible?
yes, sir.
Yes.
Uh, Sir, do we mean that the L is very small, like in the Ka by L?
So see, whenever we are looking at the phase change, we have only the latent heat of vaporization coming into the place, isn't it? There is no sensible heat we are looking at. Correct? So there is no
Yes.
temperature change occurring when we are looking at the boiling and condensation. Right? Yes or no?
Yes, sir.
So heat transfer primarily takes place only at the surface, very near where the vaporization taking place or condensation taking place. It's not occurring in the bulk actually. That's why you will see the rate of heat transfer is much larger, because the resistance offered by the medium is minimum here. Is it clear or not clear? Hello.
Yes, sir, it is clear.
Okay. All right. So a typical example is, let's say if you take a beaker, water in the beaker or even in a pan, this is the typical example, this is the typical this experience you see every day when you are making a tea, isn't it? So if you have taken a water in a pot and you are heating it from the bottom, you will see that initially some currents are formed in the water, isn't it? Correct. So there you can see the as the temperature of the surface of the bottom is about the boiling temperature of the water, then tiny bubbles start forming here. Before this, the vaporization starts
Sir,
from the surface here, top surface.
your voice
Hello,
is not so clear. It's like buffering.
my voice is not coming well. Starting from the class.
Yes, sir.
Hello. Just give me a minute. Maybe I will restart everything. So it will take. Uh, it, Maybe I'll just log out and come back again. Okay, just a minute. Hello, am I audible now? Hello, am I audible now clearly?
Yes, sir.
Hello. Now it is better or still the same?
Little bit noise is there.
Little bit noise is there, so you have to wait for 5 minutes. I have to restart everything. Okay, so just wait for 5 minutes. Don't go anywhere. Huh? Okay, I am restarting everything. So then I think it will be okay. Just give me a 5 minutes. Okay, don't go anywhere. Hello, am I audible now clearly to everyone?
Yes, sir.
Yes, sir.
Is it better than the previous one?
Yes, sir.
Sorry. So this Microsoft Teams is a lousy software. It takes huge time to start. Okay, so let me just start with what we have left. Maybe we will start from the first slide itself again. Okay, so slides are visible again to everyone. Hello, is it visible to everyone?
Yes, sir.
Sorry for the interruption. Okay, all right. So we started with the boiling and condensation. What we said is in the last class we have completed the natural convection and then we started looking at boiling and condensation. So typically in boiling and condensation, the heat transfer occurs with the phase change of the medium. And another thing which has to be noted down here is the rate of heat transfer is much higher, much faster compared to what we see in conduction and convection, typically in conduction and convection. Okay. Reason for that is in a boiling and condensation, the heat transfer activity takes place only in a very narrow region, very close to the surface. Okay. Unlike the typical conduction and convection where the heat is transferred from the surface of the medium to the bulk of the medium. Okay, so that is the difference. Typical example of boiling and condensation is just a minute. Okay, sorry. So typical example for the boiling and condensation is the condensers or the boilers used in the distillation column. Also the steam is used for heating the different equipments in the process plants. Okay. Another example which we have seen is the typical example of boiling the water in a pan, isn't it? So initially as we start boiling, you will see that the currents are getting formed in the liquid, isn't it? Further, if you increase the temperature of the surface beyond the boiling temperature of the liquid, then you will see that the small bubble starts forming at the bottom. Okay. But these bubbles, even before these reach to the surface, they collapse in the liquid itself. If you further increase the temperature, what happens is the boiling starts taking place from the surface of the liquid itself, which is called as interfacial boiling regime. Further, if you increase the temperature of this at the bottom here, then the bubble starts forming and this bubble starts moving up vigorously in a jet, something like a jet. Okay. So as you can see that as you increase the temperature, typically this is what happens. Initially, the bubble starts forming, but this will not reach to the surface. If you further increase the temperature, the vaporization from the surface itself takes place. If you further increase the temperature, then bubble starts moving up vigorously and this forms in the form of jets, and jets of this bubble starts moving up. Okay. So let's look at another interesting example. So in this particular example, what we are doing is there is a wire. This wire is immersed in the liquid. Okay, so this wire is then heated electrically, so current is passed through this wire, isn't it? So depending on what voltage we have maintained between these two ends of the wire and how much current we have passed through, what will be the heat dissipated, that we can calculate easily. Also the resistance of the wire, just by obtaining the resistance of this wire, we can find out what is the surface temperature of this wire. Okay, so the surface temperature of the wire and the amount of heat dissipated from from this wire, that we can calculate easily using the equations. Okay, so another thing is, so we start increasing the amount of heat added in this wire, isn't it? Amount of the power added in this wire, and because of that, what will happen is the temperature of this wire will start increasing. Once the temperature of this wire reaches to the boiling point temperature of the liquid, then this bubble starts forming. If you further increase the temperature, this bubble starts forming. And how these bubbles are going to form, what are the different regimes present in this particular experiment, that we are going to analyze. Okay, so typically the temperature and amount of heat, that we can modulate ourselves by increasing the current, by increasing the voltage, we can modulate how much electrical energy we can add into this wire. Also we can find out pinpointedly what is the temperature of this wire. Okay, so the temperature of this wire is gradually increased beyond the boiling point temperature of this liquid, and this excess temperature beyond the boiling point is called as T. This is nothing but the excess temperature. So excess temperature is the temperature which is above the saturation temperature of the liquid. Okay, so whatever the actual temperature of this surface is, that minus the saturation temperature of the liquid, that degree of superheat is called as excess temperature. Okay, is it clear? System is clear to everyone? Hello, is it clear?
Yes,
So in fact, you will see one such experiment in at least one experiment you will be able to see in process control, where you will be able to find out the resistance and temperature. Okay, how the resistance of the wire and the temperature is related. So if you can find out the resistance of this wire, you can pinpointedly find out the surface temperature of the wire. So that experiment you will see in the process control somewhere in the next semester or so. Okay, again, how much amount of heat we can add here, that can be varied depending on what voltage we are maintaining and how much current we are passing through, isn't it? So amount of heat dissipated is I square R, isn't it? Correct, isn't it? So
Yes.
I square R is the current. If you know the voltage, you can replace that R there, isn't it? Also you can find out the value of resistance. Once you know the value of resistance, you can pinpointedly find out what is the temperature of this wire, surface temperature of the wire. Is it clear to everyone?
Sir, what is saturation temperature here?
Saturation temperature is the boiling temperature. So beyond that, the liquid is going to boil. Boiling temperature of the liquid at a given pressure, that is the saturation temperature. Is it clear?
Yes, sir.
Okay. So again, the temperature of this wire you can modulate. Ultimately what I'm trying to say here is the temperature, surface temperature of this wire you can modulate. You can increase, decrease depending on how much voltage and current you are passing through. Okay, depending on that you can maintain the temperature of the surface. As this temperature of the surface of the wire goes beyond the saturation temperature of the liquid, what happens is the liquid starts boiling. Is it clear? Hello, is it clear what I'm saying?
Yes, sir.
And you can find out the surface of this temperature indirectly. How you can find out? You know how much current you have passed through this wire. You know what voltage you are maintaining between these two ends of this wire, isn't it? So using these values, you can find out what is the resistance of this wire. And resistance and the temperature is correlated. Once you know the resistance of this wire, you can find out what temperature of this what is the temperature at the surface of this wire, that you can calculate. So this is what is written here. You can see the measurement of the resistance of the wire can give the temperature Ts. Is it clear? So that means by modulating voltage and current, you can modulate the surface temperature of this wire. So you have that choice whether you wanted to increase the temperature or decrease the temperature. You can directly do by increasing the voltage and current. Okay. Now what we are doing, once this experimental setup is ready, we are now gradually increasing the temperature of this wire beyond this saturation temperature. We are gradually increasing. And we wanted to analyze how my boiling is going to take place, isn't it? So initially you will see that even though the degree of superheat is around 1 or 2 degree, nothing will happen, bubbles will not form. Okay. But if you start further increasing, you will see that the bubble starts forming. These bubbles starts forming, but this will not move at the top of the surface. These bubbles will get collapsed in the liquid itself, isn't it? If you further increase the temperature, there will be the jets of the bubbles forming in the liquid, isn't it? So all these regimes we are going to look at one by one as we increase the degree of superheat. Okay, so let's look at what type of regimes we are going to get. Okay, so this is the typical boiling curve. This is called as a typical boiling curve. Okay, so what we are doing here is we are plotting the log of heat transfer coefficient versus T. What is T? T is nothing but the actual temperature of the surface of the wire minus saturation temperature. So this is nothing but the excess temperature above the saturation temperature of the liquid. Is it clear to everyone? Hello? These two quantities are clear to everyone?
Yes, sir.
Okay. So now what we are doing is we are gradually increasing this excess temperature. So initially when T just equals to, that means what? The temperature of the wire is same as the temperature of the saturation temperature of the liquid, isn't it? So that is the value 0. But as we gradually increase the T, what happens initially? So section AB, this is section AB. So in this section AB, the excess temperature is less than 2 degrees Celsius. Excess temperature is less than 2 degrees Celsius. So what happens here is, in this particular section AB, the rate of vaporization of the liquid or the rate of formation of the vapor bubble is very small. So almost negligible number of bubbles get formed. Okay. However, what happens is you will see that the currents are formed in the liquid. And because of these currents, the free convection is taking place in the entire liquid. And primarily the vaporization of the liquid takes place from what? Takes place from the surface, top surface. So what is happening is, when this temperature of this wire is just 2 degree, less than 2 degree above the saturation temperature of this liquid, what happens is these bubbles will be bare minimum number of bubbles will start forming here. So almost negligible number of bubbles will be there. So almost no bubbles are there on this surface. But what will happen is there will be some currents forming here. And because of that the convection takes place. And finally you will see that in this regime, the vaporization takes place from this surface, this upper surface, not this surface of the wire. Is it clear to everyone? Vaporization of the liquid takes place from this top surface of the liquid, not this surface of the wire. And this particular regime is called as interfacial evaporation regime. This particular regime is called as interfacial evaporation regime. Okay. Okay. Is it clear to everyone? This regime is clear to everyone? Hello?
Sir,
Please go ahead.
what is meant by vaporizes only at the free top surface?
That's what I'm saying. Free top surface is this.
Okay.
Okay. So I again give you another example. When you are making a tea, remember initially some small amount of vaporization takes place from the top surface. It's not the bubbles are getting forming in the bottom, isn't it? Bubble starts forming after some time, and those bubble will also contribute in the vapor formation later. But initially, you will see the vaporization takes place only from the top surface. Yes or no?
Yes, sir.
So that particular regime is called as interfacial evaporation regime. So here evaporation taking place from this top surface. That's why this word is there. Interfacial means the interface between the air and the liquid. So evaporation starts taking place from the top surface of the liquid. That's what happens when the degree of superheat, this excess temperature is less than equals to 2 degrees Celsius. That's what we are saying. When T is less than 2 degrees Celsius, mostly the evaporation takes place from the top surface, and there are almost negligible number of bubbles starts forming at this wire surface. But when you start increasing this degree of superheat T, if you further increase the degree of superheat T, what is going to happen? So beyond this point 2, when you start increasing the degree of superheat T, actually the bubble starts forming. So this is the onset of the formation of the bubble. Here the bubble starts forming, and this particular regime is called as nucleate boiling. Why this word nucleate is used? Because nucleus of the bubbles starts forming in this particular regime. So between B and D, the degree of superheat is between 2 to 35. Between this regime, the TE is 2 to 35. So in this particular regime, you can see that the bubble starts forming, and then these bubbles move at the top. But there are also two sub-regimes are there. In this nucleate boiling regime, this is nothing but a nucleate boiling regime where the bubble starts forming. So this is the onset of the nucleate boiling regime, B, where the bubble starts forming. So between B and C, what happens is bubble starts forming, but these bubbles, when they starts moving to top surface, before they move to the top surface, these bubbles collapse in the liquid. Okay, so these bubbles do not reach to the top surface. Even before they reach to the top surface, these bubbles collapse in the liquid itself. So regime, sub-regime BC, in this particular regime, you can see that the bubbles are formed, but bubbles are not stable. Bubbles are not stable. That's what happens in this regime BC. But beyond BC, so this is between degree of superheat between 2 to 6. Between 2 to 6, this is what happens. But from 6 to 35, from point C onward, when the degree of superheat is, okay, maybe I'll just write here itself. So here degree of superheat is around 2. Here the degree of superheat is between 2 to 6. And in this regime C to D, the degree of superheat is 6 to 35. 6 to 35. So in this regime, what happens is stable bubble formation takes place. So whatever bubbles are forming, these reaches to the top surface, and then collapse at the top surface. Okay. So as you can see that, initially in this interfacial region, interfacial evaporation regime, the heat transfer coefficient is increasing almost linearly. It is increasing almost linearly, but the heat transfer coefficient increases with much more higher rate when we are looking at the nucleate boiling. Do you agree with me? Compared to this interfacial evaporation, the heat transfer coefficient, is increasing with a higher rate in this regime. Between this to this. Do you agree? Yes or no?
Yes, sir. Yes, sir.
So what could be the reason? Can anybody figure out what could be the reason?
Sir, maybe because due to more bubbles, there is more air which is insulated.
No, it's not more air.
Like,
but your answer is correct, but it is not because of air. Okay, so what happens is your answer is correct. There are more bubbles, and because of that it is there. So I will explain. So remember, in this region, the heat transfer is primarily by what? In this region, the heat transfer is primarily because of the currents formation takes place in the liquid. Yes or no? Isn't it? When you start heating the liquid, you will see that at the bottom the currents are forming, and these currents basically these currents are basically responsible for the heat transfer. Yes or no? Do you
Yes,
agree?
sir.
But when you reach to this point, what happens is bubbles starts forming, and these bubbles then move vigorously to the top surface. So if you go back here, this bubble starts forming at this surface here, and then this bubble starts moving up in this direction. So because of this movement of this bubble, some turbulence is added in the liquid. Do you agree?
Yes, sir.
And that turbulence increases the rate of heat transfer. Does it make sense what I'm trying to say? Hello?
Yes, sir.
So in this region, see here you can see the bubbles are forming, but even before they reach to the top surface, they get collapse in the liquid itself. But beyond this point, see the stable bubble formation takes place and these bubbles rise. So as you move from C to D, you can see that more and more bubbles are start forming, and again these bubbles are start moving up as a jet to the top, as a jet. The way it is shown here as a jet. Here you can see I have shown this bubble starts forming as a jet and move at the top. So more number of bubbles starts forming beyond point C, and because of that rate of heat transfer increases, and that reaches to the maximum point here. This is the maximum heat transfer coefficient. Maximum heat transfer coefficient. And this particular regime from B to D is called as nucleate boiling regime. This is called as a nucleate boiling regime. From A to B, it is called as interfacial evaporation regime. So clearly in an industry, when you are looking at heat transfer, faster heat transfer, clearly you need to operate your equipment in the nucleate boiling regime. Do you agree with me or not? You definitely wanted to work in this regime, isn't it? Because this is going to give you a high heat transfer rate. Do you agree? Isn't it? Does it make sense or
Yes,
not?
sir.
So if I'm using the boiler in the distillation column, I want my boiler to be operating at the nucleate boiling regime, because that is going to give me the higher heat transfer coefficient, and it reaches to the maximum at this point, isn't it? At this point, and the typical temperature, excess temperature for this nucleate boiling regime is 2 to 35, but better to operate in 6 to 35, because in the 6 to 35 there is a stable bubble formation takes place. Do you all agree with me? Hello? Does it make sense what I'm trying to say? Is it clear or not clear? Hello? Am I audible?
Sir,
Hello?
I didn't understand this 6 to 35.
Acha, okay, these are the typical values. I am saying these are the typical values for water. But if you change some other fluid, let's say acetone or some other, maybe this range will vary. But these are the typical values for water. This boiling curve I'm showing for water. Okay? Is it clear?
Okay, sir. Yes, sir.
So 6 to 35 is the typical range in which you will see the nucleate boiling for water. Okay. Now it reaches to the maximum value here at D. Then my question to all of you is why it starts decreasing beyond this? If I further increase the excess temperature, beyond this point D, my heat transfer coefficient starts decreasing. So what is happening in this region? Can anybody tell me? Any guesses?
Maybe because of more bubble formation, they might collide into each other before reaching the top surface.
Yes, yes, you are absolutely correct. But some more information is needed beyond this. You are absolutely correct that at point D, what happens is this formation of this bubble is so large that this bubble starts coalescing at this surface itself. And what they do is, because of the coalescence of this bubble, they form a stable film around this wire. Can you see? Hello?
So it's a kind of insulation.
So and this stable film, this film will be comprised of what? It will be comprised of gas, isn't it?
Air.
And the thermal
Yes.
conductivity of the gas is low. So that means it will act as a higher resistance compared to the earlier case. In earlier case, there is no resistance because the bubbles are start forming and these are getting detached. But once you start forming a stable film of gas around this particular wire, this act as an insulator. Can you see the point? Hello?
Yes, sir.
What we are saying is, beyond the point D, the formation of bubbles is so vigorous that this bubble starts coalescing at the wire surface itself, and they make a film of the uh, uh, gas around the wire. So this film formation starts here, but this film is not stable till this point. So you can see that as you increase the excess temperature, the bubble starts coalescing at the surface of the wire itself, and there this film get forming here up to point D to E, but this film is not stable. This film appears and disappears. This film appears momentarily and then disappears. So this film is not stable from between D to E, but from E to F, you start forming a stable film around the surface of the wire, and therefore you get the minima here, minimum of the heat transfer coefficient. Is it clear to everyone? So
Yes.
still not clear? So what I'm trying to say is, the bubble starts coalescing on the surface here, but this will not form a stable film till this point. So this film will appear, disappear, and since as you are increasing the excess temperature, more and more bubbles starts coalescing as you move from this point here. And at this point E to F, you will find that the stable film formation takes place. Stable film formation takes place here. And because of that, you get the minimum of heat transfer coefficient. This HB is minimum, this minima you are getting here. Okay, so stable film formation takes place. Now my question is, beyond this point F, then again the heat transfer increases. Why? Why? If I further increase the excess temperature, there is a heat transfer further increases. So why there is an increase? Anyone?
I think the layer will disappear.
No. So beyond this point F, you can see that the temperature is almost reaching to 500, 600, more than and at this temperature radiation starts dominating.
Okay.
So you not only have the convection, but also you are having the radiation in addition to the convection, and therefore your overall heat transfer coefficient further increases. So between this D to G, the regime is called as a film boiling, because there is a formation of the vapor film takes place. So it is called as a film boiling. Okay, is it clear? So radiation starts dominating here.
Sir, can it be possible that radiation starts occurring before this minima comes, like it goes upwards only?
So remember, this minima is coming because of radiation itself. because there is one factor which is increasing the rate of heat transfer and there is another factor which is decreasing the rate of heat transfer. There are two opposing factors are there. That's why you get the minima here. Isn't it?
Okay,
Only
okay,
one
sir.
factor is there which is decreasing, so obviously you will not get a minima, isn't it? More and more bubble formation takes place, higher will be the thickness of the film, isn't it? So therefore, actually your heat transfer coefficient should decrease, isn't it? So that is the opposing factor. But the other factor is the radiation, which is increasing the rate of heat transfer. So there is that's why this minima is coming. There is one factor which is decreasing because of formation of the film. There is another factor which is increasing, which is nothing but the radiation starts dominating. And because of this opposing effect, you get the minima here. Is it clear?
Yes, sir.
If you do not have a radiation, if you, let's say, hypothetical case, if you assume that there is no radiation, you will see that this rate of heat transfer start decreasing because the thickness of the film will start increasing, isn't it? More and more bubble will coalesce, and because of that, higher will be the film thickness around the wire, and because of that, your rate of heat transfer should decrease, actually.
Yes, sir.
Is it clear? All four regimes are clear? All three regimes are clear to everyone? Hello? Does it make sense to everyone?
So the contribution of radiation is also counted in heat transfer.
Yes. So heat transfer coefficient is, so see, remember, as I said, heat transfer coefficient is not a, it's a phenomenological constant. It's not a fundamental quantity, isn't it? It includes the effect of several factors. So even if you are having the radiation can also be included in the heat transfer coefficient, isn't it? So you are calculating the heat transfer coefficient which accounts not only convection, but also radiation, both. Does it make sense?
Yes, sir.
Your question is really valid. We have not looked at this system so far, but later on you will see that we will see some of the systems where we are calculating the overall heat transfer coefficient, also accounting the radiation. Okay, so maybe I'll just explain. So remember, we are getting the radiation QR is what? T raised to the power 4, isn't it? Do you agree with me? Hello?
Yes, sir.
And Q convection is what? So here this T14 and let's say T24 you can have. Correct? Isn't it? So overall heat transfer by radiation this, and this will be given by, let's say, T1 minus T2. But let's say if I wanted to use the same equation as the Newton's law, so my overall, if I represent Q overall, that I can represent as QH overall T1 minus T2. This I can represent, isn't it? So how H0 will be calculated? How H0 will be calculated? So this equation I can represent as HR T1 minus T2, isn't it? So T1, T2 we all know, sigma also we know, Stefan Boltzmann constant also we know. We can calculate HR. So HR will be what? HR will be do you agree? Isn't it? And this HR,
Yes, sir.
then I can add in HC, and that gives me overall heat transfer coefficient. Make sense? Does it make sense? Now I have combined both convection and radiation, and I have represented my overall heat transfer coefficient in terms of both.
Yes, sir.
Yes, sir.
Isn't it? So this HB is nothing but the overall heat transfer coefficient. I am not saying anywhere that it is only the contribution of the convection. It could be a contribution of the radiation also. That's why we are saying HB. We are saying only the B is there. The subscript B is the boiling, isn't it? So B is for boiling. Heat transfer coefficient for boiling is given by this curve. Okay. Is it clear to everyone what we are discussing? Okay. So now one more thing is there. So this is the curve when we are looking at the heating. This blue curve is when we are looking at heating. But when we are cooling down from the higher temperature, let's say 1000 excess temperature, if you are cooling down, so instead of following the same path, it follows a different path, which is shown by this dotted line. So a hysteresis is shown while the cooling. Okay. So this hysteresis is primarily because of what? When we are heating and cooling, the system is in a metastable condition, isn't it? So even though here you can see up to this, the temperature is beyond the boiling point, but still the bubbles are not forming. Why? It's a metastable system, isn't it? So while cooling, you get a metastable system with this dotted line, where instead of going up, you are getting a different line here. All right? Is it clear? Is it clear to everyone? Hello? Not clear?
Yes, sir.
Cooling occurs by radiation.
Metastable again.
Please ask again. What is the question?
What were you saying about metastable state? Please explain that.
So see, okay, I am trying to give a example here. What example I have given is, I am saying that in this region, sorry, in this region, the temperature of the liquid is temperature of the surface is higher than the saturation temperature, but still the bubbles are not forming. Why? Why bubbles are not forming? Anyone? So bubbles are not forming because even though the liquid is the surface is at a higher temperature and the liquid is superheated beyond the saturation temperature, but still this superheated liquid is at a metastable condition. Metastable condition in the sense that unless some nucleus starts forming, there is some resistance for the formation of the nucleus, isn't it? Unless that nucleus formation takes place, there will not be a formation of the bubble. Okay, so some resistance is present in the formation of the bubble. Okay, and because of that resistance, even though the degree of superheat is still above the boiling temperature, but still the bubble formation will not take place here. Now look at the same condition here. We are having the higher excess temperature here, isn't it? Higher excess temperature here. But when you are cooling down, while cooling down, it's not that the same amount of bubble starts forming vigorously. No, there will be some resistance for the formation of the bubble while cooling down, and therefore you follow a different path. You follow a different path instead of following the same path when we are looking at the heating. And this anomaly is called as a hysteresis. So you don't follow the same path while cooling and heating. Is it clear? Is it clear? Hello?
In hysteresis, this cooling is like linear. The curve is linear.
So see this increase will not take place when you are cooling down. It will directly follow this path. Because this additional turbulence which is created by the bubble formation, that will not be there while cooling down, because some resistance will be offered by the liquid for formation of the bubble as you move from here. So this, remember, at this place you will have a stable film. Yes or no? And that stable film will continue for some distance here till this. This film will not break directly at this location. This film will not break at this location, because while cooling, it will have that resistance to, retain that film. Remember, at this point, the film formation takes place only here, because this bubble will not allow the formation of the film till this point, isn't it? Appear and disappear. But when we are cooling, that stable film will continue till this point, up to this. Still not clear? Still not clear?
Yes, sir,
I
it's
will
clear.
explain one more time. Just wait. I will explain with a different concept. Heating is clear to everyone? Tell me. Heating is clear to everyone?
Yes, sir.
Okay. Now,
Yes,
in
sir.
cooling, what will happen is, once you reach this point, you are expected to break the film here. You are expected to break the film. You are expected to break the film here at this point. But this film will not be broken at this point. Why? Because this momentum which you are having till this point, this momentum will continue for some more, for a further decrease in the excess temperature. This momentum will still continue. Okay. Is it clear now? Okay, so this is something
Yes.
related to second law of thermodynamics. Okay, so in some way, the system will oppose to change whatever the configuration it is having. Okay, so that resistance is added. That resistance will be there. For instance, here you can see that there is no bubble formation. It's the system is resisting the formation of the bubble, isn't it? It starts forming here when the degree of superheat is significantly higher. So same thing is happening here. Same thing is happening here. It is going to resist the breaking of the film for some more decrease in the superheat. It will not follow the same path which is we have obtained while heating. Is it clear or not clear now?
Yes, sir.
That confidence is lacking.
Yes, yes.
Sir,
Okay.
that could be only gained if we see the same thing happening.
So have you all done your thermodynamics?
It's going on.
It's going on. Okay. I'm not sure whether this is going to be done there or not, but this metastable systems and hysteresis, etc., is usually covered in thermodynamics. I don't know whether it will be there in your syllabus or not. Okay. But typically, this type of curve you will see in the even mass transfer also you see. Crystal formation. Crystallization, when you look at the crystallization, the same path which you follow for crystallization, dissolution don't follow the same path, because the additional resistance is there from the system to change. In this case, the film formation is here and system is going to resist the disruption of the film immediately here at this point, even though it will continue some degree of superheat. It's not going to break directly at this point, not at all. That's why you get the hysteresis.
Sir, while cooling, the cooling is because of radiation only.
No, so see, we are not talking about the resistance radiation here. We are saying that we are going to decrease this T. When T is above a particular value around 100 or so, the radiation will start affecting the system, isn't it? So that's why heat transfer coefficient will increase. Okay, but as you decrease the excess superheat, the film will not break at this point. It will continue for a while, and therefore your heat transfer coefficient will be lower. Here the heat transfer coefficient will be lower, isn't it?
Okay, sir. Okay.
and it is going to follow the same linear path and it will reach to this point. It is not going to follow the path which we have obtained when we have looked at heating. Okay. Is it clear or still not clear?
Yes, sir, it's clear now.
Let's move to the next slide. So I think the figure is moved a little bit. Okay, I think this is. Okay. So next slide is this. This is the same description which we have discussed is written here. So you can see that in section BD, this section is characterized by nucleate boiling. Here the excess temperature varies from 2 to 35. Okay, from C to D, from B to 2 degree at B, and T is 35 at D. Okay. So nucleate boiling regime may be subdivided into smaller regimes. As I said, BC is the first regime where the bubble formation takes place, but these bubbles are going to collapse even before they reach to the surface. Then there is another regime which is CD. So stable bubble formation takes place here, and these bubbles vigorously starts moving as a jet to the top. So near the point D, the bubbles rise as jet or columns, and then coalescence of the vapor bubbles also occurs because of the intense motion generated in the liquid. But section DG, where the film boiling starts, happening, when the excess temperature exceeds that of the point D, the mode of boiling gradually changes from nucleate to film boiling. Here the bubbles are formed in so large number that the coalescence right on the heating surface takes place to form a film of vapor. This greatly reduces the heat transfer coefficient. The film boiling regime may be subdivided into 3 regimes. So there is a first regime is DE. So formation of the film is not complete. So film is discontinuous. It disappears momentarily and appears again. Between D. In this region, momentarily appears and disappears. So film is not continuous. From E to F, the stable film formation takes place. And from FG, the radiation starts becoming dominating, which increases the heat transfer. Similar to the boiling curve, which is given in terms of the heat transfer coefficient, a similar boiling curve is given in terms of the heat flux. Log of Qx is plotted against T. So same points you can see in this figure also. But this particular heat transfer flux is called as a critical heat flux. Hello. So this critical heat flux is very important. Why? Because remember, as I said that industrially, which regime is more important? Industrially, you should operate your equipment at which regime? Industrially, you should operate your equipments only at the nucleate boiling regime, because that is going to give you the highest heat transfer coefficient. Of course, your heat transfer coefficient is very high in the film boiling, but your excess temperature is also high. Excess temperature means you need to spend more energy on increasing the temperature, isn't it? So only the nucleate boiling regime is the most is the regime which is used most frequently in the process application, isn't it? So in the real application, you need to find out this maxima, because once you know this maxima, then you will keep your equipment operating below this maxima, isn't it? So you need to find out the flux, heat flux corresponding to this point, and this particular flux is called as a critical heat flux. So this critical heat flux you calculate very often in order to ensure that your equipment is working below this critical heat flux. You don't want it to cross this, because beyond this point, the advantage is not there. If you go beyond this, your heat transfer coefficient might increase, but then you need to spend a lot of energy in terms of excess temperature. Okay. There is also one more concept is there. So when you are having a hot pan, and in that hot pan, if you put a water, वो बोलते हैं ना पानी का छौंक दे दिया आपने, है ना? If you are thrown some water on the hot pan, what happens is these bubbles start dancing, isn't it? These bubbles start dancing or bouncing on this hot pan. This you might have seen several times if you are making something, isn't it? Cooking something,
Yes,
isn't it?
Yes,
This
sir.
particular phenomena is called as Leidenfrost phenomena. Okay. This is something called as Leidenfrost phenomena. Okay, is it clear to everyone what we are discussing so far? So I will complete this nucleation phenomena, and then we will discuss about your quiz and something on the midterm midterm feedback which you have given. We will discuss that. Okay, so I will just cover this one slide and then we will go back to that. Okay, so as I said that nucleation of the bubble is very important. Remember, as I said in the slide, unless I form the nucleation of the bubbles, nucleate of the bubbles, unless we form the nucleate of the bubble, the boiling of the formation of the bubble will not take place, isn't it? So that is very important, isn't it? So let's look at the nucleation concept little bit in more detail. So bubble formation, how? Please go ahead.
Sir, Leidenfrost phenomena will occur at the where the stable film will be formed, like in the EF region.
No, not necessary. Not necessary. In this region also Leidenfrost phenomena can occur. So this is, you are not adding the complete liquid. You are only adding some liquid droplets on the pan.
Oh, okay.
You are not completely filling the pan by water. So this is something like you have put a pan on a gas and then you have added some water on that. So पानी का छौंक दे दिया आपने. इसलिए that word I have used, isn't it? So what you will see that those bubbles will dance, isn't it? And eventually this will evaporate. But before evaporation, this will dance, isn't it? Yes or no?
Yes.
So this
Yes,
particular phenomena is called as Leidenfrost phenomena. All right. So let's look at the formation of nucleation. Okay. Nucleate formation. Let's look at the nucleate formation. So the equation used for the nucleate formation is a Young-Laplace equation. So what is Young-Laplace equation? I will just explain that. So remember, we are forming a bubble. So let's say this is the bubble formed in the liquid. So there is liquid everywhere. Surrounding is the liquid. So what is this Young-Laplace equation gives is, Young-Laplace equation gives is, the pressure here will be PV, pressure in the liquid will be PL. Okay. What will be the radius of this bubble depends on, depends on the pressure in the vapor and the pressure in the liquid. And these are related by this equation, which is called as a Young-Laplace equation. So the Young-Laplace equation is used whenever we are having vapor and liquid in equilibrium at a curved surfaces. This is very important. This curved surfaces is very important. Whenever we are having the curved surfaces, we will have some radii, isn't it? Radius of that surface, we will have R1, R2, isn't it? So what radius will be the stable radius? That depends on pressure in the vapor, pressure in the liquid, and the surface tension.
Sir,
Is it clear?
these radius will be the radius of the bubble coming up.
Yes. So this is the generalized thing I am talking about so far. So that's why I said the curved surfaces. But when we are looking at the bubble, then R1 and R2 both will be same, and this will be given by R. And
Yes,
this
sir, yes,
Young-Laplace equation simplifies to this equation. PV minus PL equals to 2 sigma by R. This is the
Sir,
Young-Laplace equation. Okay.
The R1 and R2 formula would be used when we will have thick interfaces.
R1 and R2 will be used when you are having the, it's not the spherical surface. In the spherical surface, you will have only one radius, isn't it? Correct. But let's say if you are having something like this, isn't it? So here principal radii could be different, na? Clear? Hello? So this is a generalized equation. This is a generalized equation for the curved surfaces. But for a spherical bubble, we are talking about the spherical bubble, isn't it? So for spherical bubble, this is the correct. This is the simplified formula. In this case, R1 and R2 both are going to be same. Principal radii both are going to be same as R, and that's why this is going to simplify as PV minus PL is equals to 2 sigma by R. This is the famous Young-Laplace equation. Okay.
Sir, we will use only for this like spherical one.
Yes, yes. That's why I have said this. We are only going to use for the spherical bubble, isn't it?
Okay,
All right. Again, the same thing we are discussing. As I said that the superheated liquid behave like a metastable system, which cannot go as it is for long time, and any disturbance lead to the formation of the bubble. Okay. So remember that excess temperature basically gives me what? It gives me a degree of superheat, isn't it? And this superheated liquid is a metastable. So initially, even though your degree of superheat is 2 degree, still the bubble formation is not taking place, isn't it? So it is metastable. Correct. But this system, if you increase the degree of superheat, this the system will not go as it is, isn't it? If you increase this degree of superheat, your system will not remain stable. Any small perturbation lead to the nucleus formation, isn't it? Formation of the bubble. Do you agree? Yes or no?
yes, sir.
So in the superheated liquid, the tiny bubble can form in the liquid. The tiny bubble can form in the liquid. When the tiny bubble is forming in the liquid, then it is called as a homogeneous nucleation. So clearly homogeneous nucleation has more resistance, isn't it? But if the liquid is in the vicinity of the solid surface, the irregularities of the solid surface actually helps in the formation of the bubble. And this type of bubble formation are called as a heterogeneous nucleation. This type of bubble formations are called as heterogeneous nucleation. So clearly, the solid surfaces, if are there close by, the solid surfaces, the cavities, those are present in the solid surfaces, actually helps in the formation of the bubble. And therefore, even though the degree of superheat is lower, you will see the formation of the bubble takes place in the heterogeneous nucleation. So resistance is low. But in a homogeneous nucleation, the bubble has to form directly in the liquid. There is no additional, additional irregularities coming in. These irregularities are coming in because of some perturbation or movement taking place in the liquid. That's it, isn't it? So homogeneous nucleation in general takes place at higher degree of superheat, whereas heterogeneous nucleation takes place at lower degree of superheat, because you require the less resistance is there in this case. Do you agree with me?
Yes, sir.
Even though if this is not clear, it will be clear in the next slide. Okay, so don't worry about it. We will further discuss this. So from the above equation, the pressure inside the bubble is so clearly if I wanted to find out if I wanted to form the bubble in the liquid, so clearly the PV should be greater than PL. Then and then only R will be positive. Remember, surface tension will be a positive number, isn't it? But R will be positive only if this quantity is positive, isn't it? So clearly the vapor pressure should be higher than the liquid pressure. Do you all agree? Hello?
Yes, sir.
Okay.
Sir, if it is otherwise, then no bubble form
No
can be
bubble
formed.
formation takes place. Yes, no bubble formation takes place. You're absolutely correct. Okay. Now let's see our why we are looking at this entire thing. Our to find out if there is a degree of superheat given to us, isn't it? So for instance, if I go back, here I can pinpointedly find out what is the degree of superheat, what is the surface temperature that I can calculate from the resistance. I can find out what is the saturation temperature of the liquid. So I know the excess temperature. I am asking a reverse question. What size of the bubble is going to be the stable? What bubble size is a stable size for a given superheat? That is what the question I am trying to answer. You got the point? So see, I cannot have a very large bubble here because that large bubble will not be stable. It is going to break down, isn't it? So the size of this bubble formation, depends on the excess temperature. What is the excess temperature? And this excess temperature I know. So can I find out what will be the stable size of the bubble present in the liquid? That is what the reverse question I am trying to answer here. Is it clear to everyone? Is it clear to everyone what I am saying? I am trying to find out what size of the bubble I can have for the given degree of superheat. So let's calculate that. So the pressure difference PV minus PL can be related to the liquid superheat by using the Clausius-Clapeyron equation. So this is the Clausius-Clapeyron equation where pressure and the temperature is related. Okay, so d ln P by dt is given as LV by RT square, where R is the universal gas constant, T is the temperature, LV is the molar heat of vaporization. Okay, now this equation, so see, this equation is present in this, what system we are looking at. In our system, there is a bubble is there, and this bubble is surrounded by liquid, and this gas present in the bubble is in equilibrium with the liquid surrounded, the surrounding liquid. Do you all agree? Isn't it? So vapor in this bubble is in equilibrium with the surrounding liquid. Do you agree with me? That's what the system we are looking at, isn't it? So we are having a bubble. Gas bubble. This is the gas bubble, and outside this gas bubble we are having a liquid. Isn't it? Correct. So what we are saying, the gas present here is in equilibrium with the liquid. That's what we are saying. Isn't it? If this equilibrium is not there, then what will happen? This bubble is going to either collapse. Isn't it? It's going to collapse if it is not in equilibrium. So this equation we are using, isn't it? So in this equation, we can integrate this equation between two limits. And these two limits are what? So here, let's say T1 is the temperature of the superheated liquid. Superheated liquid. P1, PL is the pressure of the superheated liquid. Tsat is the saturation temperature, isn't it? So what we are saying, that the vapor present in the bubble is in the thermal equilibrium with the liquid, and the vapor temperature will also be in TL, isn't it? So temperature of the liquid and the vapor both are going to be same. That's what happens in the boiling and condensation, isn't it? So temperature of the liquid as well as vapor both are going to be same because phase change is taking place, isn't it? Correct. So now we can integrate this equation. So d ln P, we can integrate between the limits, two limits PL and PV, because that is what is going to change. Here we are having the pressure PV. Here we are having the pressure PL. Isn't it? So between these two limits, we are integrating this d ln P. And on the right hand side, the temperature change is what? Temperature change is taking place from saturation temperature to TL. And TL is higher than the saturation temperature, isn't it? Correct. So with integration, what we get is ln PV by PL is given as LV by R 1 by Tsat minus 1 by TL. And we can rearrange this equation. So after rearranging this equation, what we get is ln PV by PL, that we can expand. Ln PV by PL we can expand as ln 1 minus this, isn't it? 1 minus this. So PL plus PV minus PL, this PL will get cancelled. We will get PV by PL itself. So we have represented PV by PL in the expanded form like this: 1 plus PV minus PL by PL. Okay. So after the Taylor series expansion, we can use the first coefficient here, this first coefficient. So ln 1 plus PV minus PL by PL can be represented by this first factor itself. And the right hand side again will be LV by R. This T1 TL minus TSAT divided by TL by TSAT. This is after simplification. But this PV by PL we can represent by Young Laplace equation as 2 sigma by R. So after rearranging, what we get is TL minus TSAT. Hello. So I will just end at this slide. Okay, we will not go again. We will recap this in the next class. But I'm giving you this information. So TL minus TSAT, if you rearrange everything, what you get is 2 sigma R TL into TSAT divided by R PL LV. And TL and TSAT, these are more or less equal to each other, isn't it? There are how much degree of superintensity is there? 5 degree, 6 degree, 10 degree. But actual value is what? Actual value of TL will be 273, 253. So even 10 degree increase is not distinguishing these two values very much. So we can use this as TSAT square directly instead of using a different value for TL. So approximately we can find out TL minus TSAT is given as 2 sigma R TSAT square divided by R PL minus LV. So from this equation we can find out the size of this bubble R. Okay. All right. So we stop here, but I will take 2-3 minutes to discuss the quizzes and your feedback. Okay. So is it okay if we go for 2-3 minutes additional? Yes. So the first thing is, if I look at your feedback, most of you have said that you wanted to have the offline quiz. Can we have an offline quiz around 20th March? 20th March is, let me just check.
Everybody will be onboarded by then, because
Everybody
we have
will
to
be onboarded by then. So
yes, we have
we
to
can
onboard.
have Monday is the 21st, isn't it? So can we have the quiz on 21st? 21st March. Is it okay for everyone?
One on 21st, and then next one will be on the April 1st week.
April 1st week, yes, yes. The next will be in April 1st week, yes. Is it okay to everyone? So that was one of the comment most of you have marked, and as I said, I take all your comments seriously. So let me just open it.
Excuse me, sir. Will the quiz will be open book, or we have to learn all formula?
Yes. Quiz will be open book. Quiz, minor, major, everything is open book. Don't worry about. I don't want you to mug up the formulas, not at all.
So we can bring our laptop,
so it will be open notes, and at max you can use this book by BK Datta. Only these two things will be allowed.
Okay, thank you.
So sir, only these two things will be allowed: the class notes and class. In fact, all these class notes are made from this BK Datta book. So if you only bring the BK Datta book, that itself is sufficient. So
sir, the physical copy and online e-copy both will be allowed.
No, not e-copy. We will not have a e-copy. We will have a physical handwritten examination.
So, sir, for that we have to print all these slide and then bring.
So, which we are saying, the physical copy of these notes you are saying?
Notes, your notes, we have to print them.
So that is why I am saying either you take the printout or you just bring the BK Datta book. So everything, all these material which I have prepared, these are taken from BK Datta book. Nothing is taken outside. So you can bring the BK Datta book, hard copy of that. That's it. That itself will be sufficient. Is it okay to everyone? Is it okay?
Yes, sir.
Yes, sir.
So BK Datta. So let's make it. BK Datta book will be the open book. Nothing more than that. Okay. Even not even the class notes, because then otherwise somebody will say that I wanted to bring my computer, I wanted to take my printout. That's not good. If I allow you to bring the computer, then there is a chance of cheating also, isn't it? What do you say?
Sir, I guess cheating can be controlled. Like we will be in like in front of you, so you can
that's why I'm
watch.
saying. That's what I am saying. I'm allowing you to bring the book, Heat Transfer Principles and Application by BK Datta. Is it not sufficient?
Sir, but your slide will be more preferable. Like,
so then okay. I don't want to pressurize the students too much. So then printout of the class notes is allowed, if that is okay.
thank you, sir.
Or someone has written by hand, so that is allowed.
No,
The same
nothing
thing
more
as
than that. Only this handwritten means you will bring something else also.
okay, okay.
So see, you have to understand the point that teacher also at some point of the time, he was also a student, isn't it?
No, sir. Actually, I had written all the notes in offline, so I was asking because of that.
Acha, okay.
In a copy.
All right, taken. No issues. But let's make it uniform to everyone. So we will have only the printout of the PPTs if you wanted to bring. But my guess is this book, this BK Datta book itself is sufficient, and it's not costlier. It's just 300 or 400 rupees is the cost. In fact, I never used to allow anything other than this book earlier. But this semester being little bit slightly critical semester, I don't mind if you bring the printout. It's perfectly all right. Okay,
sure.
so let me share your feedback. So most of you have written about this only. And I'm extremely thankful to everyone, those who have given a valuable feedback. And as I said, I go through all your comments, everything. Okay, I take your feedback very seriously. Okay, so thank you for overwhelmingly writing and giving some suggestions also to improve. Okay, we will try to improve whatever you have said. So majority of the students had said that the examination should be offline. So that we have anyway, we are implementing. Another comment was this same, whether the examination will be open book or closed book. So I don't want you to mug up the formulas and other things. So examination will be open book and open PPTs, whatever we have, whatever I have. Is it clear? So any critical comments? Let me just check. So in this critical comment, there's no any critical comment. Okay. Some more examples you want us to cover, want me to cover, but that anyway we are covering in the tutorial, isn't it? Right? So some more examples should be covered. That's what is written here. Conduction should be given less emphasis is what, but it's okay. I think we have given a sufficient time. Okay, I think everything is all right. I will try to incorporate as many comments as you have marked. And let's stop here. Sorry for extending beyond a time. Sorry. Okay. Is there any question? Can we stop?
So the first quiz is on 21 offline.
Correct. First quiz will be 21 offline. I will be booking the some examination hall. That will be offline on a paper. Okay, let's stop here.
We can bring calculator, right?